And thank you for our invitation. So I will talk about p-adic analog of multiple zeta values. Actually, so far, I gave a talk on this title several times and maybe several places. But I will introduce the definition of p-adic analog of multiple zeta values and explain its basic properties and also the relationship with Grothendieck Teichmüller group. So let me explain what the definition is, but just let me recall the definition, just complex case, usual case. Okay? This was explained in the talk about. Okay, this is an integer. When I say integers, I mean the natural number. So this is an integer greater than 0. You see the definition of multiple zeta value. Oh. Okay, this is a definition. This is a definition of multiple zeta value. I should be precise. Not MZV. This is a real number, and this makes sense when the last index is greater than 1. This is a definition of multiple zeta value, real number. Okay. I will introduce the p-adic analog of this value.
Maybe we should point out that yesterday's notation was the other way around.
Yeah.
Sorry.
So this is Japanese style.
Japanese
Oriental style. This value, okay, makes sense when the last index came with greater than 0, doesn't want. Maybe the easiest way to define p-adic analog is like that, okay? This is just rational number, see? So just consider in the topology of QP and consider it summation in the topology of QP. This definition might be very, very nice. This is quite plausible, but unfortunately you cannot give a definition of p-adic analog by this power series. Why? The reason is quite simple. You see? So here, okay, among these birds, you can find power of prime p. Okay, p is going to be prime. You just consider its inverse, yeah? So in the topology of R, this goes to 0 if n goes to infinity. But here, in the topology of QP, okay, this goes to infinity. So this power series, this infinite summation never converges, because there's a subsequence which goes to infinity. So you cannot give a definition by this summation. So why don't you think about, say, consider the condition prime to p. Then you can avoid this situation. But still, you cannot give a definition of p-adic analog of multiple zeta value by this power series. Okay? If ni is prime to p, that means this number ni is a p-adic unit. So this is a summation of unit. This summation, each term never goes to 0. So you cannot define by this summation. So okay, in real number, in real setting, we are very happy you have this definition of multiple zeta value. In real world, we are really happy. But on the other hand, in p-adic situation, we are unhappy. you cannot define by this power series. To achieve this, we need a kind of new idea to define. So let me explain how we can give a definition of p-adic analog of this value. To do that, we consider this function just a polylogarithm, or it's a multiple version. G to N. This is, let me call this is one variable. Multiple, let me call this function multiple polylogarithm. Shortly denote MPL. Here G is complex number. This is a multiple polylogarithm function. My tail. This is my tail. In G is here, G is complex number. In complex case, you can show that this function converges inside open unit disk. What's the relationship of complex usual multiple zeta value and multiple polylogarithm? Okay, this value is just a special value at the point 1. This is a specialized value at the point 1. So let me explain more precisely. This function converges open unit disk centered at 0. 1 lies on the boundary and is a kind of limit value. Limit is multiple zeta value. So I will employ the relationship this. We consider the p-adic multiple zeta value. Here we replace C by Cp. What's the Cp here? Cp is a p-adic analog of C. The definition is okay. Qp, you consider Qp. Take a completion. This means the first one is algebraic completion. And this is topological completion. We have a p-adic variation unit, p-adic distance, and take a. This is we say Cp. Cp is a kind of p-adic analog of complex number. The definition of p-adic multiple polylogarithm is just replacing C by Cp. This is a p-adic multiple polylogarithm. And what's quite interesting is that you can also prove that this converges inside open unit disk. Here, what's this distance? This is p-adic distance, multiplicative valuation. We need more arithmetic treatment, but you can prove that this function also converges inside open unit disk. This property is a common property, not only between complex case and p-adic case. Yeah. So in complex case, you see, you can consider the limit value to the point 1, and you will get multiple zeta value. We want to do the same things, but here comes a problem. In p-adic case, okay, you can consider the open unit disk centered at 0 and the open unit disk centered at 1. These two are actually disjoint. They are disjoint. I can explain you why. Okay, this is a set Cp. And this is they are disjoint. I can explain you why. they are disjoint. Okay, this set, okay, we have a OCP, ring of integer, this reduction map, right? This set, all the elements of this set goes to 0 if you take reduction. But here, all the element of this set goes to 1 if you take reduction, okay? So if you take reduction, these two goes different. So that means they are completely disjoint. In complex case, we are happy. We can consider the limit value to the point 1. But p-adic case, some unhappiness happens. I mean, 1 is a kind of bit far. 1 is far away from 0. We can't consider the limit value put to the point 1. So what should we do? We have to make an analytical continuation. And now, from now on, I will explain how to make analytical continuation of this function and how to consider its limit value. That's my short introduction. So I will explain how we can do that. It's a kind of, let me recall the P complex case. Okay, complex case. Just to take a differential of this function, multiple polylogarithm, k1, km, g. If you take a differential, you can easily see that the last one, minus 1. If km is not equal to 1, and if the km is equal to 1, we can show that small n minus 1 km is equal to 1. This is an inductive differential relations among multiple polylogarism. And the first step is monologarism. Okay, Li1g. If we take differential, this is equal to 1 over 1 minus g. This is the differential relations among complex, one variable, multiple polylogarism. It's quite easy to see that this also holds for a p-adic setting. Why? You see, we have a power series expansion of multiple polylogarism. Both complex case and p-adic case both converges open unities. And this differential equation can be checked just by direct calculation. So it's quite easy. This differential equation is a kind of common property between complex case and p-adic case. That's important. This is really important for the analytical continuation of multiple polylogarism. So let me explain how to make analytical continuation, p-adic multiple analytical continuation of p-adic setting. But let me recall complex case. Okay. This can be achieved by making a kind of back calculation of this differential equation. We have a monologarism. Okay. This is originally the function defined inside the open unit disk, but we can make an integral expression starting from 0 to g, 1 minus t to dt. And actually this is equal to minus log 1 minus t. This was originally the function defined only the open unit disk, but once you get the integral expression, you can make analytical continuation beyond the open unit. This is the analytical continuation monologarism. And next, you can do the same way, dilogarism. Dilogarism is again 2d ai1t dt over t. Okay? So this is the kind of iterative integral expression. This monologarism was analytically continued. So you can, and you have this integral expression. So you can make a analytical continuation of dilogarism. the analytical continuation can be done inductively. See? Using dt over t or dt over 1 minus t, you get the kind of, let me write abbreviated iterated integration starting from zeta t, and you only need two differential forms. By using this, once you get a iterated integral expression, you can make analytical continuation. I'm just to review the wave analytical continuation. This function was originally the complex function defined inside open unit disk, but you have a iterated integral expression, then you can make analytical continuation. Analytical continuation to where? Actually, the huge space. 0, 1, infinity, and of course, this is not true. This is the universal covering. This is our issue. This is the story. So, as the log has infinite branches, each multiple polylogarithm, analytically continued multiple polylogarithm, has several branches. Infinite branches, okay? Countable infinite. For example, the log has many. In complex case, each multiple polylogarithm was previously defined on the open unit disk, but you can make analytical continuation, and you have infinite, countably infinite branches. This is a complex case. So next, let me explain the p-adic situation. P-adic situation, we need some work. Several in p-adic setting, several integration theory has been settled. But here, I want to particularly employ special integration. Employ Robert Coleman's integration theory. This is established in 1982, I believe. So this is a really heavy theory. So I don't want to explain the full, but I just want to give a special remarks. I'm a kind of special cohesion on this theory. His integration theory is attached to some parameter. Before he constructs integration theory, he attaches some parameter, which is called branch. Attached to a branch. So let me denote say A of p-adic logarithms. What's a p-adic logarithm? P-adic logarithm is just a function from just CP cross group homomorphism plus CP plus group locally analytic group homomorphism from the multiplicative group to additive group. This is called p-adic logarithm. P-adic logarithm is not uniquely determined. There's a several choice of p-adic logarithm. But one set take a thing, it actually depends on the choice of parameter. Here's a special element p. Once you fix an element, image of p, then p-adic logarithm is uniquely determined. There's a quite formal argument. So normally we denote log another color A. Once you fix the image of p, say a, then p-adic logarithm is uniquely determined. And this is really important. In the first step, before he constructed his integration theory, he fixed a branch of p-adic logarithm. And then later, he created his integration theory. So his integration theory is heavily depends on a choice of branch parameter. This is really important. That's my question. For the construction, it's really heavy. But I don't want to explain. But this remark is really important. I will explain how we can make a. How to make analytical continuation by using his theory. Although we have to fix a branch parameter. Yeah? Continuation, analytical continuation of multiple polylogarithm can be done almost the same way. So let me explain. Where's my yellow chalk here? Yellow chalk? Okay. This is p-adic, okay? We have a p-adic monologarism. P-adic monologue was introduced this way. This is defined only for open unit disk, but we can make analytical continuation. We have an integral expression, yeah? So you can make a back calculation. You have a differential equation, so you can make a integration. Integrate by Coleman integration. This is Coleman p-adic integration. What's this? So this is nothing but minus log 1 minus 3. Because this one. And my special caution is that we are fixing a branch parameter a, so this is attached to a. Okay. P-adic monologarism function defined inside the open unit disk. But if you make analytical continuation by using the integration theory, you can make analytical continuation of bigger space, but it heavily depends on the branch parameter a. I note that when G lies on the open unit disk, then in this case, in that situation, this is free from the branch parameter. If you make analytical continuation, if you make analytical continuation beyond the open unit disk, there's a many way. And we are now fixing specific branches. So anyway, let's keep on. We have this analytical continuation. What's the next? Next should be dilogarism. We have a p-adic dilogarism. This is function defined open unit disk p-adically, but you have an integral expression here. We are using p-adic integration. But if you have a p-adic integration expression, you can make analytical continuation. Okay? This is you extended, so you have a here. We need a here. So once you have an integral expression, you can make analytical continuation, but depends on the branch parameter a. Completely the same argument works to above. So by imitating this method, iteratively, you will get the integral expression of p-adic multiple polylogarism, starting from z, dt over t, and dt over 1 minus t. But once you have to be careful that this depends on the branch parameter. If you let a values, you will get another function. The branch parameter a is really important. But anyway, if you fix a branch parameter, you can make analytical continuation. Analytically, p-adic analytically continuation of p-adic multiple polylogarism. Okay, I have to explain. To where? Okay, in complex case, this can be analytically contained in the universal covering, but p-adic case, you can make analytically continue. You don't need to take a universal covering, just 1 and infinity. That's the difference. Why there is no zero? because at 0 we have this power series expansion. It's quite easy to see this is analytical at 0. But 1 is real specific, and infinity too. This corresponds to the pole of these two differential forms. This is the situation. And I have to remark you again that this theory itself depends on the branch parameter, so I should put A here. The situation is like that. Inside the open unit disk, this is a quite branch-free region. But if you make analytical continuity beyond the open unit disk, then it's heavily based on the branches. One more comment. So anyway, you have a branches. Branch corresponds to branch parameter A. So this is, in this case, uncountably infinite branches. Okay? The reason is that because cardinality of CP is Aleph. So in complex case, countably infinite branches, but in p-adic case, uncountably infinite branches. Situation looks similar, but sometimes it's a bit different. So this is how to make analytical continuation. Yes.
Can you explain why you did not delete 0?
Hmm?
Why don't you delete 0?
Why?
Why you don't
Oh, you
want
delete
to
0.
zero?
Okay. This is definition of p-adic multiple polylogarithm. Z belongs to CP. And okay, this is analytical at the point 0, right?
Yeah,
Yeah, so it's easy. That's why I delete 0.
but in the complex case,
In complex case,
you have monodromy and
yeah, monodromy,
so
but
you do have
you
to
can
delete
make,
zeros.
you can make multiple polylogarism. You consider the multiple polylogarism. Complex case, can we delete 0 here?
Yeah.
No, I don't think so.
No.
If you make analytical sum, log z,
Yes.
log appears. So
why is it not the case in the p-adic case?
So p-adic case, the reason comes from different because we don't need to take universal covering, right? This is one reason. And
Well, why don't you need to take
why you need
Why
just
does it need to
this
take
power
universal?
series expansion tells that this is not analytical at the point 0.
You could say
Hmm?
Results about this, which are unique, monodromy one. The theory of Coleman integration.
no, A is fixed.
Yeah, yeah,
The
yeah.
monodromy, there are special paths in Coleman integration that picks out.
So, but maybe if A is a parameter, it's kind of analog of this
No,
universal
A is
covering.
fixed. A is fixed.
Yes,
Yeah, but if you view it as a parameter also,
Mm.
then it kind of becomes E.
Okay, suppose we have a pole. So pole is something like a log pole, right? Right? And log pole. So log should be depends on the branch parameter A, right? But at the point 0, the open unit is set at 0. This is a branch independent region, and just given by this power series.
Yeah.
Yeah.
No, I understand it's independent of A.
So
Okay.
oh, okay,
Well,
sorry. Can I keep from?
yeah, sure.
Hmm. So let me explain this. 1, 2, 3. Let me recall the relationship, the p equal infinity, multiple polylogarithm, and multiple zeta value. So, okay, we have a multiple polylogarithm function. Just I'm explaining the complex case. This is the complex value function. So you consider the limit. This function, where g belongs to c, and you just consider the limit by a prime. Prime means you just consider the limit in the original Riemann sheet. this limit, okay, converges or diverges according to if Km is not equal to 1. And actually this limit, when this limit converges, this is exactly the multiple zeta value. This is, you get the multiple zeta value. This is a complex valued function. So we know this is a real number, but anyway, let's see. So let me explain what will happen in p-adic situation. P-adic situation. So I will use it. We consider the p-adic situation, okay? Multiple polylogarithm, p-adic multiple polylogarithm is a p-adic function originally defined inside the open unit disk. But I explained how to make analytical continuation. Yeah? But you need to fix a branch parameter A. Right? If you make analytical continuation here, otherwise one might be poor. And here C is replaced by Cp. And you can consider the specific limit. So what will happen to this function? So my theorem also needs some work, but what I have proved that here, this limit converges if the Km is greater than 1 for any branch parameter A. So the analog property holds in p-adic situation. This is holds for any A. I have to give some remark. Complex case, when the last component Km is equal to 1, then this limit always diverges, right? But the p-adic situation actually not. I can't tell. This is kind of missing. I have an example this diverges, and also I have a counter example. I have an example which converges. So this case is kind of mystery. I can't tell what will happen. This holds, but this I don't know. Maybe more work should be required. So my definition of p-adic multiple zeta value is exactly the relationship of these two. I will define the definition of p-adic multiple zeta value is the limit value when the Km is greater than 1. This is a p-adic analog of multiple zeta value. So C is replaced by Cp. Yeah? And I notice that I fix a branch parameter A. Yeah? So I should put say here. This is a p-adic value lies on Cp.
Where does it live?
Cp.
Is it in ZP?
ZP. I will explain some more, but I can say Qp. So we may say something on denominator, but perhaps ZP, but I don't know. I can't tell. We can say Qp, but ZP may need works. I don't know. This is a definition. So I have to introduce the several property of this value. One of the important property of my definition of p-adic multiple zeta value. So this is okay. This value is quite natural value, number 4. My result, this is a bit different story, so it's that. This my definition is free from branch parameter A. P-adic multiple zeta value is free from any branches. Okay, this function, this is a special value of analytically continued p-adic multiple polylogarithm. This is a CP value function. This function admits many, many branches, actually, uncountably infinite many branches. But if you consider the limit value to the point 1, they take the same value. So it's a kind of quite natural value. What's quite interesting that, okay? You consider the point 1 minus epsilon. The special value as 1 minus epsilon. If you let A values, they take all value of CP. But if you consider the limit to the point 1, all value takes the same value, all branch same value. Only the point 1 is quite specific point. All the value takes same value. So this is some. So this explains. This theorem might say that my value is a kind of quite natural value. I have to explain the several property, but okay. So let me explain some property which was also related to the Francis Brown's questions. So let me recall the p equal infinity case. You see, multiple zeta value. This is okay. Special value of multiple polylogarithm, and this is a C value, complex valued function. So according to this relationship, you can say this is a C. But actually, multiple zeta value is a real number. We have the same property. The p equal, when the p equal finite prime, when the p is a prime number, you have a definition of p-adic multiple zeta value. This is special value of CP valued function. So a priori this is element of CP, but actually you can show that this is a QP. So this is the property. So you can consider kind of limit, p-adic limit of rational numbers. I don't know. And so this value is free from branch, and this actually is the element of QP. I have several remarks on this value. This is an example. Okay.
Free even independent. Free even independent.
Independent. Yes. Independent of, yes. This English is better. Independent of independent of any branches. Anyway, they take same value. I have several examples. What's this value? So, okay. The special case is okay. So, okay, so in complex case, I have some extension. We have very famous formula, zeta 3 equals zeta 1, 2. In p-adic case, we can prove this relationship. Zeta p3, zeta p1. This is a question. We can prove the same. This is proved by Euler. Huh? We have a p-adic analog of Euler's relation. Zeta 2, 1, okay? So this case is infinity, so what's happened in the p-adic case? This actually converges. We can prove it to minus 2 zeta p3. So this is, I think that's that is 2. Yes, 2, 1. Here, in this case, this is this explains this situation. The last component Km is equal to 1, but it converges, and converges to specific value minus 2 zeta 3. So the situation looks quite similar, but sometimes it's a bit different. So I should explain, okay? In complex case, this is also proved by Euler. You can consider the zeta 2k. This is some rational multiple of pi 2k. What happened to p-adic situation? P-adic situation, this is a really interesting example. You can consider the 2k. They are all 0. Something.
So the disk is something rational.
Disk.
I think you've drawn something, a disk.
Yes, yes. Okay. Some rational number, very or okay. Okay, somehow. P-adic situation, all even value becomes 0. So we have no pi here. Let me explain why we get it. We can show that zeta pk is equal to p2k minus 1 pk. This is p-adic function constructed by Kubota-Leopoldo. This follows from the result by Coleman. We can prove this. And once we prove this, this is immediate. Because when the k becomes even, this becomes odd character. And it is quite well known that p-adic function with odd character is identically 0 function. So you get this one. We have no pi in p-adic situation. 1, 2, 3, 4, 5, 6, 7. I will also explain some conjecture. Okay. This is explained in Cerveret's talk. You consider the space of multiple zeta value. I'm explaining the dimension conjecture whose weight is equal to W. So this is subspace, linear subspace of real numbers. There's a dimension conjecture. Sorry?
The constraint is what?
Weight is equal to W. I should explain more clearly. What's the weight? M values. You consider that this is the real value, and you can consider this is actually this set is infinite. So this is a finite sub-vector space, finite dimensional vector space. This dimension, you can consider the dimension. This should be equal to dw, where dw is equal to minus 2 plus. This is dimension conjecture due to Zagier. This is by Zagier. This is a conjecture. ちょっと狭く今回とか。As a result, Dorin Goncharov Terasoma, what they prove that the upper bounding holds. This was this is a complex case, the dimension conjecture. We can consider p-adic setting. We put zp0, p is prime. We can consider space, p-adic multiple zeta value, blah, 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 all the way to qp. There is a p-adic dimension conjecture, so I should relate p-adic. p-adic variable. P-adic case GWP is equal to DW minus 3. The reason is that because we have more relation. In complex case, we have a pi, but in p-adic case, all pi is going to be 0. So the dimension is a bit smaller. And actually, by using some Tanakian argument of the category of a mixed state motif, we can prove that this is equal to W minus 3. This is a p-adic dimension conjecture. And this one, completed by the same argument, by using the complete p-adic same argument, this bounding was shown. We have a dimension bounding. As for lower bounding, we don't know. But anyway, so I can tell more. I have to talk about some GT matters. Let me recall just the complex case. Complex case, okay. I want to skip many story, but Drinfeld considers the KG equation, and by using KG equation, he considers two fundamental solutions like this. And by using this, he constructs what is called Drinfeld associator. By KG AB. AB just non-commutative formal power series, and which is called Drinfeld associator. And it is known that there appear multiple zeta value each coefficient. Plus more regularized terms. This can be constructed by Murakami's method. Murakami's regularized terms. This is a well-known story in Drinfeld associator. Drinfeld considers KG equation, and he constructed special two fundamental solutions. By taking a quotient of these two solutions, he came to define the Drinfeld associator. And as it was explained in Elbert's talk yesterday, there appear multiple zeta value like this. Multiple zeta value appears. This is P complex side. I did the same way. I work in the p-adic, introduced the p-adic KG equation, and I have introduced the two fundamental solutions and consider its quotient. So this is CP, OCCQP. We can, by imitating Drinfeld arguments, which he done in p-adic case, complex case, I have introduced a p-adic analog of Drinfeld associator. What's important is that each coefficient is a completely same way. P-adic multiple zeta value appears. Oh, yellow color. This is p-adic. We have a p-adic non-commutative formal power series with QP coefficient, and where each coefficient there appear multiple zeta, p-adic multiple zeta value. we have a p-adic Drinfeld associator and p-adic multiple zeta value. What Drinfeld has proved is a pentagon and hexagon relation. This is number, which one? Number 9. Number 9. In p-adic complex case, you consider, say, phi kg AB defined. So this is just a changing of parameter. A divided by 2 pi I, B divided by 2 pi I. This is also the C coefficient. But Drinfeld has proved that phi kg belong to M1C. Say, I employ the associator. I employ your notation. Drinfeld proves that Drinfeld associator satisfy pentagon and hexagon equations. This was shown by Drinfeld. We can prove the p-adic situation. I have a definition of p-adic Drinfeld associator, which I denote phi kgp. Okay. You can show that this satisfies pentagon hexagon action. But this is not a set of associator that is GRP1. This is, as is explained, QP. This is the result, Umba, and also I gave a more technical. You can show that p-adic Drinfeld associator satisfies pentagon action, but it's not the set definition. It's not the defining relation of associator, but the defining equation of graded glutamate integral. It's a bit different. Let me recall what's happened. So, in let me recall what's the relationship of set of associator and set GRT1.
So can one prove this from Yamashita's method?
So
does it follow immediately from,
this one?
yeah. Does it follow from, does Yamashita's proof imply?
Maybe your result will imply no, but what your result might imply. No. So the technical thing is somehow we have to construct the realization factor, and we should explain this is so will behave under Tanakian formalism. Yeah, that's the technical part, and he claims that he did that. Yeah. Okay. GT acts from left. Sorry. In your, according to Professor Don Bantan's talk, GT1 acts from left and set the associator, and GRT1 acts from right. And a set of associator forms a bitosa, and from which you can show that GT1 and GRT are isomorphic, non-canonically. Right? What's happened? Okay, so set of associator, you consider C value point. We have C value point. We have Drinfeld associator. If you consider QP value point, you have a p-adic Drinfeld associator. You see? Gauss theorists usually talk about GT instead of GRT. The reason is that because you consider the QL value point, we have a Gauss action, Gauss group, Q bar to Q mu L infinity. We have this Gauss action. Okay. So my impression is that GT1 one kind of arithmetic interpretation is that GT1, okay, set of associator is a bitosa. GT1 acts free and transitively from left, GRT acts free and transitively from right. My impression is that this is GT is a kind of Galois side, and this set of associator is a kind of, say, period side or multiple zeta value, or say Hodge side, and this is a kind of p-adic side or p-adic crystalline side. That's my impressions.
So you don't need CP, it's really C in the middle.
In the middle is C. In the middle is C. This is a Drinfeld associator, so should I use C, right? This is the picture. P-adic side is p-adic Drinfeld associator is not associator but element of GRT. Drinfeld associator is a really associator. This is and Galois group map to GT. So we have a three words.
You have to embed QL into C somehow, or
Embed the Q.
so it seems strange that you have something act.
Oh, yeah,
QL.
so this is QL, this is C, this is QP. We don't assume L on P. L on the prime is quite independent. L can be equal to P, but because this is C, this is QP, this is QL, so we can't. I think we can't combine, mix together. I have some specific remark, maybe some difference. The last one, number 10. This is Drinfeld argument, okay? In complex case, we have an associator and 5 set of associator, and this is the GRT tosa, right? We have a special element 5 kg. This is a complex number. We can also consider just complex conjugation, or you take the complex conjugate of all the coefficients. Because you see, GRT associator set is a GRT1 tosa. That means there is a unique element G, which means that such that phi kg y is phi kg with G action. There's a unique element. So you can take a logarithm. This is unipotent. By taking logarithm, you can identify with nilpotent real algebra. We have a log G. And this is a graded algebra. So you can get some number. And actually I prove that this is, and M is all odd integer. This is called the Drinfeld element. This is called Drinfeld element. Drinfeld constructs a specific element, C structure. And I have a remark. Because Brown proves that this algebra contains a Freire algebra, so this phi m generates free sub real algebra. BGRT. This is a consequence of Brown's result. We have some specific generator, but this is not rational. This is a C structure. We can imitate this argument.
Before you erase that board, before you erase that board, does the form formula there
Mm.
of information about the F's from Lashak's talk. Can we translate that formula for phi of k squared in terms of 1 plus p-adic zetas into something about the F's from the action of the Galois group of Q bar over?
So you mean that absolute Galois group acts on here?
I mean, the absolute Galois group acts on pi 1 of p1 minus 3 points like in the talk
The
yesterday.
one thing to let act, yeah, we have to factor through set of associators, right? But set of associator, we have some nice element, but this is Drinfeld associator. This has a C structure, so you can't do that. Once you fix some nice element, then you are able to do that. But I don't know.
Okay,
Maybe.
I'll think about it.
It's true that if you take the l-adic projection of the F sigma yesterday, then that's what the Iara was basically investigating.
Is
in
the
many
first
papers.
formula come from that formula, the one that
No,
gives
no,
the-
that's
No.
I also have a question with this formula, because you said that the zeta values, they are this function that you have introduced with z equal 1.
Yeah.
But so if you just take the same formula for arbitrary z, what you get, is it also an associator? Does it satisfy the pentagon?
No, the one is special. One is quite special. Oh, maybe using this blackboard is better. Sorry. Yes?
As far as we know, you can't deduce anything about the F's from Pierre Lachac's talk yesterday from that formula, even without the P's in it. Is that the state of the world now?
So I couldn't catch. So because this side you are talking this side, and you are talking about Galois side. It's quite this side.
Maybe in a vague way, small the story of the Hodge side and the Galois side. And the zetas would correspond to Soule characters. And the Soule characters would be in the
They
l-adic.
look like the
So
actually, I'll ask you guys later.
Maybe later is better. Actually, my talk is almost finished, but just let me explain. Complete the p-adic situation. P-adic case, we can do that same argument, but actually more easier argument, because I did explain that here, GRT1, p-adic Drinfeld associator is an element here. So you don't need to twist by complex conjugation, it's directly. You can take a logarithm, B, GRT1. So you can take a logarithm, then what you get? You will get, this is graded algebra, so you will get the p-adic analog of Drinfeld element. Well, one thing quite important is that here, okay, this is that. Drinfeld, because he twisted by complex conjugation, so all even disappear, only odd appears. But in p-adic case, I didn't switch anything, so this is Drinfeld construct a nice element for only odd degree. But if you work p-adic setting, we can get odd degree also, but we have also even degree specific element. I don't know that. So phi 2k plus 1 should be the analog, p-adic analog of complex setting here, but for 2k, I don't know what is. Might be something. I think that this is one important, one thing remarkable difference between complex case and p-adic case. So my talk is over. Thank you.
So, is there any question?
you never mentioned double shuffle.
Double shuffle, because double shuffle is a consequence of pentagon, right? So I missed it.
Oh, so
Yeah.
by your theorem.
Yeah.
You mean
Thank you.
you prove that it's
Yeah,
valid
yeah.
and that your theorem is valid.
I didn't understand one point when kind of you first claim that f PKZ is associated.
PKZP is associated.
And then
Yeah.
you claim it's an element of GRT1.
Yeah, it's element
It's
of
a
G.
general phenomenon, they're the same, or these two sets are the same, or what?
So generally.
They are just identical. Associated, p-adic associated and GRT1
Yeah,
are
yeah.
the same. Is it a claim, or
Yeah.
is it just happens?
Yeah, just a theorem, just a theorem. This is a theorem. So it's okay. This is a theorem by Umba theorem. This is a theorem by Umba and also myself. This is a theorem by Greenfeld. Oh, okay. Yeah. So, I mean, we check the pentagon and hexagon equations.
But it's not true in general, right?
What do you mean general?
I mean, these two sets of associators and the set of that's a group, right? Essentially, if you forget origin and GRT, you get associators, right?
Yeah.
Unit, forget. So. I don't understand. I mean, still equations are different.
Maybe, are you saying that it's a torsor with a trivial rational point in the p-adic case?
In the p-adic case, so this shouldn't be, I think this shouldn't be rational. So sorry, so
this is a group. This is just a set.
this is just a set. Yes, this is just.
Yes.
This is a set. This is a group. Okay.
Yes. Are they identical in p-adic case or not? I mean, like how to say identical? Of course, I mean the sets are identical. As I said, you choose an origin, and this is the same.
Now I understand. My writing is really confusing. Okay. So now I understand. Okay. QL never acts on C. Okay. This is Drinfield's result, right? Yeah. This is all the Drinfield result, right? Yeah. But what I have constructed element, this is not C structure. I have constructed the C structure. Okay. This is a rational, and Galois group map to GT1 QL. I should write here. Okay. This is, and this is all the very different things. Okay. This is the Drinfield's theorem. Okay. The associator set is by 2 the GT acts from left and the GRT acts from right. And what I have constructed QP structure, the element of QP structure. Drinfeld constructs the C structure. And if we consider QL structure, Galois group acts on it. Of course, we cannot relate these three at the same thing because QL and C and QP are all different. Yes?
At the very end, you asked this question about psi P2K.
Yeah.
Do you have an example which is non-zero?
Which is non-zero. I can't prove zero. I can't prove non-zero.
There's no canonical.
So I don't know, isn't it? Yeah? It's difficult to prove non-zero.
Do you make a conjecture that this Lie algebra is really generated by this element?
So this is conjecture. This is conjecture to be. And Francis Brown's result is that it contains a free Lie algebra.
Yes.
That's
Yes.
conjecture to be
There is
called.
this conjecture in the classical case.
Yeah.
Do you make the same kind of conjecture in the p-adic case?
Okay, the conjecture is over rational, right? So yeah, you don't matter whichever. The conjecture is over rational numbers, right? So just to take a scalar extension, QP or C, it doesn't matter.
Okay.